Okay, so our interest is in still the flow problem. We're interested in looking at transient behavior. We made the case before that when we look at this system of equations, it's actually a subset of the full set of equations that we could imagine. That might be something like this, where the h's are vectors, the others are, and the q's are vectors. For steady state, it's only this leftmost term and the rightmost term. For transient behavior, we have this capacitance term, which in solid mechanics would be kind of a damping term on displacements. And we don't have the equivalent in this system for anything that deals with what would be the equivalent of the second derivatives, which are accelerations. They have no real equivalent, I think, when we're talking about heads. It would be d2 dt squared, so we don't actually have those. And so when we're dealing with these, there are two things that we have to do. We have to come up with whatever this capacitance matrix is, or the storage matrix, and we talked about that last time in terms of what the components were. I guess we figured out that the magnitude of this storage matrix looked something like a parameter multiplied by an integral, again, over the volume of the shape functions, like this, in its broadest form. We made the case also that if you look at this integral and you are able to take this storage term outside, then this is just the volume of the element, nothing more. And so if it's a triangular element, we only did it for a brick element, but if it's a triangular element, it would be equal to, well, you know the volume is going to be equal to the area of the triangle times the thickness, whatever that is. In our particular case of the one-dimensional element is just the product of the area of the element and its length. And so we talked about how the different components of that, where they sit in the matrix as consistent mass or lumped mass, merely allow us to say if there's a change in the nodal condition of head, how much fluid gets squeezed out from that tributary area. If it's a consistent matrix, then it comes from both nodes, both ends of the element. If it's a lumped matrix, then it comes only from the node where the dependent variable changes. Head changes at node 1, then fluid comes out as a flux in a time step at that node. And that's the physical meaning of it. And so once we know what these matrices are, the other problem we have to deal with is time integration. And we went through an example by basically being able to write our matrix equations either at t plus delta t, or at t, or at any point in between. And we call this one implicit solutions. And we call this one explicit. And we solved an example using the implicit one last time. And so today what I thought we'd do is we'd take the other end of the spectrum. We go to look at the explicit one by writing a similar set of equations but at a different location. Solve it. There are some intrinsic disadvantages in doing it that way, and there's some intrinsic advantages, and we'll talk about those. And actually those advantages and disadvantages kind of divide around this middle point here, this 50% mark, where you write the equations at time. This is t plus delta t over 2. This would be delta t over 2. And so, well, the punchline is that if you write the expressions on this side of that, then they are only conditionally stable. If you write them on the right-hand side of that, they're unconditionally stable. And based on that, the solution method varies slightly. So that's where we'll go with this. Okay? So let's get back to, we'll maybe come back to our solution from last time. So, what do? We start off with the same equation. The equation, as you remember, we said is exact, but physically what we're doing is we're writing it at some location which is the first point here. So we're writing it physically at this point here, where the head is head at t. Of course, we can write the head at any particular value that we can call tau, right? We mentioned that last time. And that represents some time that we'll also call tau rather than t, right? So this is the point here. We can write this equation at tau at any particular point. We're going to choose to write it at this particular location now, in which case it's written at time t. Heads at time t we probably know. The rates of changes of heads at time t we certainly know over this interval. If we project to this point here, this is, I suppose, head at time t plus delta t. We can write them at individual nodes, or we could think of these as a whole vector of properties as well. And so if we calculate the rate of change of head over that segment, actually, irrespective of whether we write the equations here or here, over this linear segment, the gradient of head, change in head with time, is going to be the same. So it doesn't matter if we write it at time t plus delta t, or if we write it at time t, the magnitude of this parameter is the same because it's just a linear line, a linear relationship between them. So we have this expression. We're going to want to be able to use this. What else do we notice? Well, the other thing we notice is that we could choose to write this in lumped form. If it's written in lumped form, I'll just swing back, not too far. But you remember in lumped form, all it means is that we add the two terms on all the terms in each column together and put them on the leading diagonal, in which case we only have a one-dimensional matrix, a vector if you like, with zeros everywhere else. And of course the inverse of that matrix is just going to be 1 over each of the individual values. Victor, yeah?
I have a question. What is the significance of the SS factor?
Which one? What?
If you go back to, when you define the S matrix, there is an SS factor.
Oh, SS is the physical property, specific storage.
So like
It's like compressibility. So in petroleum engineering, it's basically a compressibility. By definition, the specific storage is the amount of the volume of fluid that's squeezed out of an aquifer per unit volume of the porous media per unit head change. So it's just a property, physical property. You'll see that when we talk about thermal problems, then the equivalent behavioral term is just the product of the density and the specific heat capacity, if that means anything. So if we write this as a lump matrix, then the inverse of that matrix is very simple to get. You don't have to invert it. It's just the inverse of all the terms on the leading diagonal. And so what it allows us to do is to be able to rewrite this matrix by taking this term over to the right-hand side, multiplying both sides by s minus 1, I guess. If you multiply both sides by s minus 1, then you get exactly this relationship here. And so this is just a rearrangement of that. It's only possible to do it easily if this is going to be a diagonal matrix, because it's the inverse of it is trivial. And then what we want to do is be able to figure out exactly what the magnitude of this rate of change of head is. And the rate of change of head we could write in graphical forms, obviously. If you go back to this, this is ht. So in other words, the head at this magnitude here, at ht plus delta t, is just equal to this magnitude plus this gradient. This is delta t, delta h. And so this is just by definition the gradient. So if you multiply this gradient dh dt by delta t, so this here is delta h over delta t, which of course, if you look at this figure, is a physical property. It's the slope of that line, which we want to be able to define. And so if we know what this is, and we multiply it by the time step, by definition, this term here is just delta H. In other words, just multiply these things out. So we think that then we can get the magnitude of this new parameter here, which is this, which we don't know. If we know what this initial head is and what the gradient of this head is, so if we know what this is, and if we know what this property is here. And so the calculation sequence is basically at the bottom. So let me just make it smaller so it all fits on at the same time. So we calculate what our matrices are for these different functions that go in here, the conductance matrix and the storage matrix. We calculate what the gradient of head is from this expression here, from the magnitudes of the existing heads and also the appropriate relationships. Once we have this term here, we can substitute it into equation 4. If we know what the previous head is, if we know what the gradient is and the time step that we choose, we have an update. We take this update and we put it into this expression here. That's physically the calculation step. And so that allows us to kind of increment each time step to be able to go. And so you'll notice a couple of things about this. One is that it's only going to work easily for us because we have an inverted matrix here. If this is an easy matrix to invert, and of course if it's a one-dimensional matrix it's trivially easy to invert. And the second one is, which we haven't demonstrated yet, is that it's only conditionally stable. And so the implicit method was unconditionally stable. We could choose any time step we wanted to and we'd actually get a stable result. Wouldn't necessarily be the correct result because we have to discretize quite finely in time and in space to be able to get that. But we'd always get a result that wasn't wildly oscillating, for instance. If you choose the wrong time step, too large a time step in this particular case, then you'll find that the solution just oscillates, maybe oscillating with in a damped form that it damps out, but often oscillates and gets larger and larger in an undamped form and never gives you a proper solution. So that's the deal. And so these methods fit into two different categories. Unconditionally stable can take as large a time step you want, but with much more overhead if you're doing nonlinear problems to be able to reform the conductance matrix to be able to do this. And explicit methods, which are much better at dealing with nonlinear problems, because the overhead in changing these matrices is somewhat less, because certainly changing the storage matrix is trivial. Certainly changing the conductance matrix is a bit problematic. But if you're solving the system anyway, having to use time steps to be able to follow maybe nonlinearities in the behavior, then there's no real problem in using an explicit method because it's actually cheaper to solve than using implicit. Okay. So you remember last time we did a quick problem with two elements to solve it. Let's do exactly the same problem, the same as before, but using this different method. You'll remember that we started off with just two elements to define the height of this thing. You'll remember that the geometry was one where we started off with the heads were uniform throughout the thickness and equal to 1, and then at time equals t0 plus we set this one equal to, whoops, it's moving because it senses something else. So this is t equals 0 plus. In other words, we change this boundary condition on the top node. This is t equals 0 minus. So before we change anything, it's just this one uniform head throughout the system of magnitude 1. And then all of a sudden we change it at this particular node and it will respond. And it will respond so that over time, in theory, it will look progressively like this. And at time infinity, if we hold this value constant, this will be like this, t infinity. But we also know that because we only have two elements here, we're not going to be able to capture all of this nonlinearity, this parabolic, this curved, quadratically curved shape on this. It'll just be two segments of a linear distribution because of the nature of the elements we use. Okay. So, what do we remember? You'll remember that the conductance matrix, or maybe you won't remember, but I remember, that the conductance matrices were 1, -1, -1, 1. You may or may not remember that the storage matrix was equal to, I guess, 1, 1, and this in its lumped form. And so the matrices then you'd get by putting conductance matrix here for element 1, conductance matrix here for element 2, likewise for the storage terms. The term here is just the sum of the two ones that happen to coexist at that particular location. We've jumped ahead by realizing that this value of head at node 1 is equal to some magnitude, and multiplying these terms and taking them off the right hand side. So this is the one term that comes from there and the one term that comes from here, from each of these. And we've done the same for this value here, which is the head at node 3. I think this is node 3 here, and I think this is node 1 here, as I recall. And so we've done the same with this, and I've taken these terms out, and we end up with these. This is -1, and this is +1, hence the plus h and the minus h3 there. And so those are the components we have. And that's basically our matrix equation that we have. Same as before, this is fixed. This is originally 1 and now 0, so that's also fixed. So we only really have one degree of freedom in this system, which is this central node at node 2. And so the only equation that we really care about is this middle equation between these two not very well drawn horizontal lines. It's supposed to be bounding this. And so we only really have one equation. And so the equation, if we look at it, is just this central equation. And what is it? It's this. So yeah, it's actually written out here. So 2 times h2. This is 2. 2 times the rate of change of h. It's not a question mark. That's a number 2 in each of these. This is a flux. Since we're not prescribing a flux, it's equal to 0 because mass in, flow mass in has to equal mass out as one of the internal conditions. And the values of head are the magnitudes we change it to. This is changed to 0, and this one here is kept at unity. So this is the only one that will change. And of course it's multiplied by the value of the K matrix. So this is just, each of these are just multiplied by 1s.
Question.
Yes, go ahead, Victor.
So this assumption that the internal Q's are 0, wasn't that only for incompressible systems?
This is an incompressible system except for the storage, and so in steady state the compressibility at those nodes will be given by there still has to be no mass accumulation, but there can be exchange between stuff coming out of storage in one location and going into storage in the other location because the heads will change. And so all of the compressibility, if you like, of the system is accounted for that in that capacitance stream.
Okay, so we can
always assume that. Yeah. Okay, and so that's the single equation. And so what we want to be able to do is, instead of write it in this form, we can rearrange it to be able to get this rate of change. So if you can imagine taking equation 2 and what? I guess you subtract this term off to the right hand side and then multiply both sides by 1 over s, which is really what we're doing here. That's exactly what we've done for this expression here. But we haven't put in the term, so this is exactly this expression here rearranged. And so this is our storage term, sorry, our conductance term. This is the only term that we will have here, which is 1. This is 0, as we said before. This is, as we just discussed, always a mass balance or a volume balance in our system that we're dealing with here. And 1 over the storage matrix for this simple element is just 1 over 2. And so the two important relationships we have are that we can get now a magnitude of the gradient as a function of whatever the head is. This is going to be the head where? Which node? It can only be node 2, right? It should be, yeah, it's this term here, right? So this is storage. Am I saying that right? Yeah, no, this isn't storage. So this is this term here, H2. This is the magnitude of the head at the central node. And so this will change from time to time, right? It starts off at 1, and once you've done one iteration, it'll be slightly less than 1 and bigger than a half, I guess, based on this geometry here. And so it'll be another recurrence relationship where, depending on this term, and this term will always be the same, this is always 1, this is always 0, this is always 0. So actually it's a very simple relationship to evaluate. We can calculate the magnitude of the time rate of change of head. Once we have the time rate of change of head, we have enough to be able to calculate from what the head was at node 2. These are the values at node 2 at the previous time. This is the updated value. So it's no more than that. And so you can work through that just as a recursive relationship, and you can choose a number of time steps. You'll notice that the time step before, when we dealt with implicit models, you remember that the time step actually went into the matrix relationship. Right? So if you wanted to change the time step, you'd actually change this effective conductance matrix, which is part of AX equals B. So this matrix here, which is kind of this one, is one that would change as a function of your choice of time step. Now our time step doesn't have any bearing on the matrices that we use, and so it can be changed to be able to accommodate maybe rapid desaturation or rapid changes in fluid pressures that occur for some reason or another. And so that's one of the advantages of using explicit methods rather than implicit. So I haven't walked through it with a table in this particular case, but if you use this recursive relationship, and again this is a really have you guys ever drawn a graph by hand? Oh, do you ever use log paper? Who's used log paper here? Oh, okay, fine. So I don't feel so alone now. So this is log paper, obviously. But this is the system. You probably can't see this very well either. But you can choose time steps to use. And the time steps for this one are 0.100th and 0.1. And if you do that, you get these. So these must be the results for 0.01. These are in here. And you get this particular curve here. If you use time steps of, actually that's not right. So that's not right. Here's, if you use a time step of 0.1, I guess we could try it. Why don't we do it? I think that would be the first value, right? So if we use a time step of 0.1, what do we end up with? We start off with this value of H2, let's say H2 is equal to 1. So if H2 is equal to 1, we have minus 2 times a half. Then this gives us a value of the rate of change of head at node 2 is going to be 2 times 1, which is 2, minus, negative, divided by 2, which is 1. So this is equal to minus 1. And then if we use minus 1 for this, and 0.1, then we have minus 0.1. I guess this, okay, I guess, what do we get? Do we get 0.9? Is that right? This would be minus 1 times 0.1, which is minus 0.1. This would be 1, so it would be 0.9. So yeah, so the value you'd get if you use 0.1, I guess, would be 0.9. Actually, that's exactly kind of what you get. If I count up here, this is 0.5, the steady value. 0.6, 0.7, 0.8, 0.95, is that right? So I guess 0.1 is not used. Am I doing that correctly, or am I doing something wrong? I'm trying to read this, and it looks to me like this is 0.01. And it looks like if your first calculation, am I leaving out a factor of 2 somewhere for any reason? I don't think so. Oh, anyway, so. Sorry? Which one? Oh, yeah. Okay, I didn't do. Yeah, okay. Thank you. So that's 0.95. That's exactly why, right? So this is actually 1 over 2. Thank you. That's exactly right. And so this is minus a half. Yeah, that's exactly right. This term here, I didn't pull in. And so it's 0.95. Yeah, so this is right. So if it's 0.1, then the magnitude you get is 0.95. So this is the first calculation. I guess the next one would be for 0.2, which would be, I'm not going to do the calculation, I think is it this term here? This would be 2, 3, 4, 5, 6, 7, no, this is half. This is 0.2 here. So if you do the calculation for the next time step, it should come out to this. So if you do it for any time step which is smaller than 0.1, you actually get, they'll all fall on the same curve, which is this main curve here. If you do it for a time step, I don't see it for 0.5. Certainly if you do it for delta t is equal to 1, what you end up with. So delta t is equal to 1. What's the rate of change of head is going to be equal to, this is still 1. This is minus 2. Yeah, does anything change? I guess not, right? Because there's no time components there. So it's still the same gradient. And so now if you use a time step of 1, then the revised head is going to be 1 times minus a half, which is minus a half, which is, we'll take this from being 1 to being a half. So the value, if you use this, gives you the first value of head at node 2 is equal to a half. And so I think that is exactly this little square here. So if you do it for delta t equals 1, you end up with this. And I think if you do it for all the subsequent values for 1 extra second, another extra second, it just it flatlines. So it gives you actually the right result, curiously, but it's, I guess, yeah, but it's prematurely the right result because it shouldn't be that low yet. And if you use a number bigger than this, which I think is what this is, I'm guessing that this value here is 0.2, so you perhaps can't see this. But if you, well, let's try. What happens if we then use a value of time step which is equal to 2? So if we use delta t equals 2, then we end up with 2 times minus a half, which is minus 1. Minus 1 plus 1 is 0. And so if you look at the value for a time step of 2, then the first value is at 0, which is down here. And then the next value is at 4 is at 1. I think the next value is at 0 again, and the next value is at 1. So it oscillates between those two. And so you get a result which is dependent on the size of the time step you use. And so that is kind of, well, it's a reasonable enough demonstration of this difference between implicit and explicit methods. Conditional stability and unconditional stability. So this is only conditionally stable. Choose the wrong time step and you get the wrong result. If you use a time step larger than 2, I imagine it would oscillate uncontrollably and move away. And so those are two ends of the spectrum. And we'll do a little example maybe with EGEEfem just to illustrate that. The other thing we mentioned that you could do is that physically what we're doing, if you recall, is that we're writing our system of equations somewhere between these two locations. either time t or t plus delta t with some increment. And the heads of those are appropriate defined. We could also write it at some point in between, in which case the head would be at some point tau. And we can do that if we just scale this value. I suppose the magnitude would be equal to some length here that we call lambda. Yeah, lambda, some length here. And so when lambda is equal to 0, the head, if this is equal to 0, obviously the head is equal to the head at node t. When lambda is equal to 1, so it's really a scaling parameter rather than anything else, then this is equal to 1, we subtract this, and then the only term we have left is this head. And so the head at this intermediate location is equal to t plus delta t, which of course it has to be at this point. And so the only interest in using this arrangement, this multiplier or scalar, I guess, it's almost like a shape function, right, that allows you to choose the point where you want to reference partway in this range between t equals, the time is equal to t and the time is equal to t plus delta t, and it just scales with those magnitudes. And so what we can do then is we can write in general the expression that we had. We said that this expression is correct wherever we wish to write it, anywhere in this interval. It's absolutely rigorously correct. What we could do is if we want to write the magnitude of this gradient as well is the same any point that we choose between these two locations also, because it's just a straight line that we're assuming links them. So this maybe esoteric way of doing that allows us to be able to substitute back into this for magnitudes of this and magnitudes of this, which allow us to be able to write out this expression, which is absolutely correct, writing it at time tau, but we write it now in terms of the times at each of the particular locations. And so the one reason for doing that is to realize the fact that we're not limited to writing these expressions at these endpoints, but we can also write it anywhere in between. And we may or may not want to do that, but often we want to write it halfway in between, where lambda is equal to a half, for the reasons that are mentioned here. We won't prove it, but the best results that you can get in terms of time stepping and with the minimal errors that you get from doing it are if you write it at the midpoint, so-called central differencing, or named after its originators, Crank and Nicholson, when lambda is equal to half, which are different from the two cases that we've already talked about. Backwards differencing, which is what we've called implicit. Forward differencing, calculate the magnitude here and project forward, is what we've called explicit. And the magnitudes that you get if you write in the middle are actually of higher order accuracy, and you need to do that in some problems. We don't need to do it for the flow problem, but when you look at transport problems, sometimes you have to use central differences. And so this is the other reason for defining this behavior in terms of this lambda term, is that greater than half, greater than and equal to half, all of the solution methods are unconditionally stable. They'll be like the first one we did. Choose whatever time step you want. You might not get the right answer, but you'll get a stable solution. If you choose a time step which is too large and you're using one which is below Crank-Nicholson of lambda less than a half, then you'll get this oscillating behavior. So that's the time stepping methods. Of course, I couldn't resist doing this with EGEEfem just to be able to cement those kinds of views. So let's try solving the same problem and do a couple of things. The couple of things are, is you recall that this is just a one-dimensional problem with 3 nodes and 2 elements over some length 2. The other thing to remember is that what we've said about the real behavior that we expect to get, we expect it would look something like this curved response. clearly if we're using only two elements, the best we can do of representing that curved response would be in going from this to this. Let me draw a line here. To this, to ultimately the straight line. So of course you realize why, if this is 1, that the steady value at the midpoint needs to be a half, for obvious reasons, right? Just that's a steady flow condition. But if we're trying to represent it, we'd only have these linear segments of this little portion of the curve. So let's mess around with our description of what we need to be able to apply to be able to solve a problem. Well, you'll remember this, the code that does the execution. Let's not worry about this. All of this goes into the conductance matrix. It's all localized. So you're solving a problem, maybe 5,000 elements, a million elements, whatever. You take one element at a time. You go and compute the conductance matrix for that and the storage matrix. You then put that in the global matrix, and then you go incrementally through all of the other elements and do exactly the same. And so it's localized in a single element at a time. And so this is the element matrix. We looked at this before. So it sends backwards and forwards potentially these 4 matrices, 3 matrices, can't count. Conductance matrix, the capacitance matrix, which is our storage matrix, and the mass matrix, which doesn't exist in this particular case. It's these ones that we first kind of mentioned here. So this one doesn't exist, but this one, so this is, I guess, KL, L for local, I think. This is capacitance, local, and this is mass, local. So it's done for each of these portions, and it's done locally. And the magnitude of it is just here. So it turns out that it's really just this one line. Whoops. Don't want to do that. It's just this one line here. And you've seen that, for instance, it's a lumped mass matrix. It has to be in the particular way that we solve it, at least in the explicit case, because we don't, yeah. Even if I put, so if I wanted to put a consistent mass matrix in there, it would look very similar, right? It would look like what? Remember? It would be the same, but what would it be? It would be, I think it'd be this, right? Is that right? Yeah, right. So these numbers together would have to add up to 2, as it did here. So it's just the appropriate weightings on these. And so it would give us something. I don't really have anything to draw on now. I've done this. I guess I do, right here. So in other words, if you recall, the storage matrix was equal to either specific storage times volume multiplied by a third, a third, a sixth, a sixth. Or if we added these two terms together, then it would be equal to specific storage, volume, and a half, 0, 0. Nothing more than that. And so it just gets localized in the same element subroutine. We haven't had to integrate them or do anything fancy with it to get it, but we end up with those numbers existing there. Nothing more than that. And so I'm not going to do that. I'm going to get rid of that because I don't want to mess with it. But I think that's right. Yeah, it's got the factor of 2 here, and so it's correct. Right. So we got that. What's our input? Our input is nodal coordinates 1, 0, 1, and 2. So the elements are of length 1, and there's 2 of them. It's this particular element subroutine, which is the 1, 1, which we call, it's just the name of our element. And it has a hydraulic conductivity, has a cross-sectional area, and it has a capacitance. So this capacitance term for us is specific storage. And so in our particular case, conductivity, area of the element, can be any number, it wouldn't make any difference. I guess it would on the storage terms. And the magnitude of specific storage, I think we said was 2 for the problem. And it's the same for both elements. And so in other words, our system is going to look like this. So very straightforward. So I guess it's this. I don't draw very well. This is nodes 1, 2, and 3. This is representing heads that originally look like this, 1, 0, and this one gets turned down to this one immediately. So this is t equals 0 plus, t equals 0 minus. What else? We know that this head is always equal to 1. We know this head is equal to 1 and then goes to 0. And we know that this head here is equal to 1 and goes to whatever it should be. That's the calculation, right? The only calculation we're doing, the only free parameter we have in this particular case is this middle node. And so if we do that, then we can go back to this little data center. Node 1 is fixed head. Node 2 is internal. So the fluxes are set and they're 0. And node 3 is a fixed head, which is always equal to 1. This fixed head starts at 1, right? But it goes immediately to 0. And so it just turns out that the calculus of this little routine assumes that the initial heads are 1 and then they go. It just happens. It's not put in any more logically than that. So the boundary condition at the top node goes to 0 from 1. This one is a flux and it's 0. And this one is a nodal value of head and its value is equal to 1. So it's just honoring the conditions. I can't actually get both. Perhaps I can. It's just honoring the conditions that we have for this particular geometry. So in other words, this would be here, the index that we apply. This is a head value, so this is a 0 index. This is a flux value. We're solving for this head, so this is a flux index, and this is a head value, so this is a head index. So that's the values of these terms. Have I got it backwards? I guess, no, that's right. I guess I did get it backwards, right? So where heads are fixed, it's equal to 1. Sorry. Heads are fixed, they're equal to 1. Fluxes are fixed, it's equal to 0. Heads are fixed, it's equal to 1. So I was lying to you all along. So that's what these is. So the kind of boundary condition and the magnitude of that boundary condition. And so that's it. So you just need this extra component in terms of the conductance matrix. And I think then the only thing to change in this is you have to make sure it gets the right data file. And I think as you go down the screen, we've never really talked about the guts of how this works, but I think what exists here is this. So here we go. So there's just a switch in the system. So if we're solving static problems, which we've done so far, we've set it equal to 1. If we're solving flow problems dynamically, we set it either 2 or 3 depending on the problem we're solving. So I just set it at 2 for solving this implicit case. There's a time step in there of 0.1. And yeah, if you look at these things, you'll see some expressions which start looking similar, right? This matrix here looks like our K-star matrix, solving our K-star matrix. No, let's not worry about it. Let's instead run it and see what we get, because there's some utility maybe in that. So run it. Where's this? Oops. So let's set it equals 0 first. I think, doesn't that clear this? This clears the screen, I guess. So let's run it for our particular case and see what it gives us as we go to the top. It comes up, so all of it are 2 by 2 matrices. It calculates the conductance matrix. That certainly makes sense. It calculates the storage matrix. That makes sense. It puts the conductance matrix in the 3 by 3 matrix for the global conductance or stiffness. It puts the conductance matrix in the global 3 by 3 matrix, just the first 2 terms, for the S matrix. Takes in some other information. It does it then for the second element, conductance matrix, capacitance matrix. It put those 2 extra terms into the global matrix, so it puts 1 minus 1 minus 1 in here, and it puts in 1, 0, 0, 1 on the bottom term here. And then that's the matrix it ends up solving to be able to give us the magnitudes of the unknown. And so the only unknown we have is the value of the head at the middle node, which starts off at the first time step of 0.1 as 0.95, second time step 0.91, 0.87, 0.845. So ultimately it should asymptote to 0.5. It's getting there. Yeah, so this value here is 0.52. If we ran it slightly longer, I suppose, there must be a set number of steps here that it does. So I guess one way to get there faster, the easiest way to do it, we could change the number of steps. We did it with 1, right, in here? And what was the first value when we did that? I think it turned out to be, wasn't it 0.95? I guess we go back. So if we run this for that value, hopefully it doesn't crash. We'll see that the first answer we get as we go down through here, same processes as before, was 0.75. That doesn't seem to be what we got. Is that right? What's different in this case? Are we using the right storage matrix magnitude? The damping is 1220. Anyone see an inconsistency in what we're doing? Conductance term we had was definitely on the leading diagonal was 2, so I don't see inconsistency with that. The value of the conductance matrix is 1. So yeah, so anyone see obviously what's different? I know I'm the one who should actually know it. It is implicit. It is a time step of 1. It does start at 1.0. Yeah, that's curious. Okay, so I won't waste all of our time figuring that out now. But the other thing to see is that ultimately when you goes to time infinity, the magnitude of that head, or the displacement, right? So you remember that when we're looking at problems and we're solving this matrix equation in terms of all of structural mechanics, we work in terms of displacements and forces, and so that's just the way that this is kind of written. I've written it that way. So the displacement U versus the value for the force. So this F is Q and the U is H in our terminology. But ultimately the magnitudes of heads we get in the system as well.
So I think you're using the implicit in the example we did.
Yes, that's right. Okay, so yeah, okay, so that's right. And so okay, excellent. So that probably is the reason. So the coding might not be wrong. Yeah. So we'll look at that next. Good point. So the magnitudes that ultimately asymptote to being 0.5, and they've already got down to this magnitude. So let's do exactly that then. So we can change this to, yeah. Kill these, so we just look straight at it. do it. So, implicit, explicit rather. In the previous case, we end up with the same matrices. Okay, for 1 we immediately get 0.5. And that was right, I guess, was it? That's what we get. Yeah, okay. So, that's right. And let's do it for, what was, yeah, we used it for 2. And was that the oscillating one? I thought it was. And after you get these results, you see that the magnitudes are, so yeah, so the first value is 0, second value is 1, third value is 0, fourth value at 8 is 1, etc. And it just oscillates obviously between the two magnitudes. So if you physically looked at the case where we have this, I guess, then it would start off here, it would go to here, then it would go back to here, and it would just switch between those. And that was in terms of time, the trace that we did, our trace was only starting at 0.5, and so it would go basically. If we do it for a bigger number, like 5, let's see what we get. Or let's just double it to 4. And we do it again. Oh, there you go. Some big numbers, you see. So you see the numbers already. I saw a number that had about 10 digits in it. So I think that's a bit off our plotting scale. Solution switch, time. So what's it do? First one is +5. No. First one is -1 at 4. Second one at 8 is 5, +5. Third one at 12 is -13. Fourth one at 16 is +41. Fifth one at 20 is 121. And as you go down, then this is the number we end up with, right? So it grows. And so instead of doing this, obviously it's doing something like, and so the meaning of conditionally stable is shown. So anyway, so an interesting exposition of that. So I suppose the take-home points are, one, that the other thing that we get here is only a magnitude of the value at the middle point, and it will always look exactly like a bilinear response. And so it will never capture the true behavior that we expected. And so you only do that if you're able to put in more elements, in which, of course, you could do that if you so wanted to. I won't waste our time doing that here. And the other one is that depending on the time step you use, it's either, or the method you use and the time step, it's either conditionally stable for this lambda less than 0.5, and it's unconditionally stable, but not necessarily the right answer if lambda's equal to half and larger. So I suppose we could, if we, I don't know if we have time to do this. Let's see if we have a connection to hammer. I guess, does this work? I was thinking about putting boot camp on my machine this weekend, but didn't. Decided that I'd try and use the network. This does not have a network connection. Oh, it is doing that. Okay. Well, let me also remind myself of what I need to do. I have this little thing here. So what do I need to do? Module load Comsol 3.5a. Okay. This one, backslash, or the other one? Guess it will tell us very soon if that's the case. It likes it. So let's see how quickly or slowly it runs to be able to deal with these. Oh yeah, okay. Guess it's waiting for me to tell it what it wants to do. I think that's right, isn't it? Yeah. All right, so it's the old one, but let's see if we can do a quick example. Could be Earth science model. I prefer diffusion. It's a diffusion equation we're dealing with. So it's transient analysis. So you see this. Let's do our one-dimensional problem, I guess. So we need to make a brick. So let's do the brick vertically between plus and minus 0.4. Let's do it 1, 2, 3, 4. Actually, it doesn't matter how tall. I guess we could do it the same height. That may be a challenge for me to do it. But let's not worry about the height. All right. Let me see if I can remember. All right. So what else? So what do we have to do? Options, constants, physics, I guess. Subdomain settings, what's it need? So in our particular case for our group, it needs some material for hydraulic conductivity, which was 2 for us, or 1? 1? Can't remember. It doesn't. It needs. So this is the equation it's solving. It needs a value for storage, which operates on concentration or head. This is the conductance matrix on concentration, which is head. And so we've chosen both magnitudes of those of 1. I guess this was actually 2, wasn't it? It doesn't really matter. Is that right? We need to apply some boundary conditions. We need to be able to see those boundary conditions. So let's put the boundary conditions on the side as equal to no flow. So the boundary conditions on the side we'll set to insulation. In other words, no flow. The boundary conditions on the top we'll set to, bottom we'll set to concentration, which is the same as head. And our particular magnitude of that head was 1, right? At the bottom. And on the top boundary, which is this one here, we will put a head of 0. Okay. It's going to need initial conditions, I guess. It's going to take initial conditions of 0 if we don't supply them. So, okay. Does it need, I guess, subdomain settings, right? Initial conditions of 1. And we're going to run it, but I guess we want to be able to do time stepping. So times are, so this is the initial time, 0, time to time 1. And so let's not do time 1, but let's do 10. And this is the time step, which is 0.1. And so that's, I think that's all that is. And I'm guessing that we could, it'll mesh itself, but if you just let it do that, it'll look like this. And if we run it, it will solve a system of equations exactly for that. And so this is at time 10. And the magnitudes are what? Sometimes it's easier to see these if we draw a graph. So is it domain plot parameters, global cross-section plot parameters, right? So if we draw something for the concentrations, which are the heads, so it's an extrusion plot. The extrusion is between, this is x is 0 and both the x's are zeros, right? Just to do a vertical section up through it. The y starts out as minus 0.8 and ends up as plus 0.8. I think if it does 1, it'll be fine too. Yeah, okay. And so, disappear. And so this is the cross section. This is the top that initially starts out as equal to 1 and gets drawn down. So this is the top here. Starts off at 1, and then all of a sudden this one goes down to 0. So you get this t equals 0 plus behavior, which is this top blue line with a little instability in the top as it has. This is the first time step, second, third, fourth, fifth. So you can figure out, since we're doing time steps of 0.1, this would be after 0.1 of a second, 0.2, 0.3, 0.4, 0.5. The final value is this linear value, which is at time t infinity. I suppose we could compare our system almost between the two, right? I don't know which particular solution mode it's using. It's chosen one on its own. But we could at least do a ballpark comparison of our solutions with EGEEfem, right? What were the last ones that we did? Well, I guess we know. We know from this that the solution with 2 elements, it should be done by, this is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. Well, it should be done by 10 seconds. And I guess it's saying that, indeed, by the time 10 seconds is done here, if we show this, so this has to be, it was for time step of 10 seconds. Certainly by the time 10 seconds is done, it's reached steady state. If we did it for just, if we ran it instead for maybe a smaller time, so I suppose this, it's not going to ask us. Okay. If we ran it instead for 1 second, so it'd run 10 times, and we run it, and we plot that same plot, then it suggests that we're almost at steady state as well. After, so this is 0.1, I think, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, no. So this is 0, I guess. This is 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9, 1 second on the blue, if you can see that. And so in all of these things, I guess we'd want to reconcile it as to whether it makes sense. I don't know whether if you put more elements in it, and of course if you look at the geometry for this and the elements that we have, clearly it's not just one element at mid-height, one element at the top. The other thing is that it's also a different geometry, right? So let's see if we can change that. How are we doing for time? Oh, we're almost up against the wire.
I have a question. So
Yeah, go ahead, Victor.
why is Comsol using this non-uniform geometry?
It's using uniform geometry. What do you mean by non-uniform geometry?
Non-uniform, just not regular.
Because they're not uniformly distributed?
Yeah, so why, for example, here below you have this one?
It's because it's automatically meshing and it uses some algorithm to do it. You can prescribe it so that it actually has a regular rectangular grid. And in some cases that you, for instance, where you want to be able to reference how the material properties change at a point, you might want it to be exactly with a regular grid.
No, I guess the real question is this an improvement on grading techniques using in this fashion?
This is a coarse mesh, so I'm not exactly sure. Certainly you can make the mesh finer by refining it. and refining it, and also, whoops, I guess I'm going back, and also I think maybe I think this allows you to refine it in certain areas. Yeah, so you can refine it in different ways depending on where you think you want to do it. But there are a variety of meshing techniques that you can use. There are a variety of elements that you can use. This has just chosen a volume, an area filling element. I'm trying to think where it would be. Don't use it so often. If you look at the subdomain settings, actually, yeah, here it is. So some of these things would make sense to you now. It's using shape functions which are, instead of well, I've got to go somewhere sometime. So instead of using linear shape functions, I think it just chose these by default. So it has some default parameters in. And so these are actually the orders of integration that you use for the Gauss points. 4-point quadrature, I think, for the conductance matrix. I think this is 2-point quadrature for the capacitance element. You don't need to use such high magnitudes. And this is just some code. So you can actually use elements which would actually have quadratic. Highest order shape function is x squared, cubed to the power 4, or to the power 5, depending on the problem you're solving. So I don't know if I answered your question, but it's chosen a specific system to deal with. I won't have time to change it. But obviously, much more sophisticated mind than EGEFEM, but that's